Okay, today we're talking about Chapter 8, Section 2, the inverse functions. So inverse functions it's definitely something that you've seen before, but another one of those that you kind of probably just tucked away in those memory banks of yours. So let's get some definitions out of the way, or avoiding mistakes. That's a big one. Okay, looks like we got tons of definitions today. And let's just go ahead and wrap it up with the horizontal line test. See how far I get. Okay. And you know what? Let's just go ahead and snip the first example. You know what? Actually, also, I think it's best if I also just go ahead and snip the solutions here. That way we can actually see the horizontal lines that we're making. All right, so we got a lot of snipping done there, and that's the lecture. No, but anyways, so introduction to inverse functions. So a function is a set of ordered pairs x, y, such that for every element for every element x in the domain, there corresponds exactly one element y in the range. Okay, so we know that that is the definition of a function, right? However, what is an inverse function? Well, it does literally the exact opposite, actually. Okay, so where are we at? Okay, so if we have a function 1, 4, 2.5, 10, 4, 16, these are the points on a graph. Also, you know, if you plug in an x, or I'm sorry, if you plug a 1 in for x, you get a 4. If you plug a 2.5 in for x, you get a 10. If you plug a 4 in for x, you get a 16. Well, an inverse function performs exactly like you think it would. Okay, we're talking about, you know, instead of having the ordered pair 1, 4, we're going to have the ordered pair 4, 1. Instead of having 2.5, 10, we have 10, 2.5. And instead of having 4, 16, we have 16, 4. Now, this avoiding mistakes is a huge, huge deal because, again, this is a mistake I made because, again, when I was going through this, I didn't care about math. But now I do, but this was a mistake that I made, right? So f, and if we raise it to a negative 1 power, that doesn't mean a negative exponent, right? So the notation is precisely being used here. It is an established notation that if we raise a function to a negative 1 power, it just means inverse function, right? Now, again, the notation for exponents or honestly just any numbers, it's clearly defined that if you raise those to a negative 1, then yes, it is a negative exponent. But if we are denoting a function's name raised to a negative 1 power, that just means the inverse function. So the definition of a one-to-one function, it's, well, honestly, let's just think about it, right? Let's just think about the idea of something that is one-to-one, right? Something that is one-to-one, well, for every one, there is another one, right? So let's look at these two examples, and again, these are pretty easy examples here. If we have some elements here in the yellow and some elements here in the blue, okay? We can call them elements in the x, elements in the y. Well, notice how uh, two of them go to one element in the blue. Okay, so since there's not one going to just one, then it is not a one-to-one function, right? Um, we can also see this is not a one-to-one function either because we are going to different elements. All right, this is actually not even a function, is it? Um, well, if you recall in previous sections, we did something called a vertical line test to test if something was a function graphically. Okay, well, on the other side, there is another test we can use, and it's called the horizontal line function. I'm sorry, the horizontal line test to see if something is uh, an inverse function. I'm sorry, a one-to-one function. Let's see if something is a one-to-one function. Okay, so let's go ahead and look at that. Oh shoot, never mind. Not yet. Not yet. Sorry, I forgot to snip this. So using a horizontal line test, we can use the horizontal line test to determine if something is a one-to-one function. right? And then never mind. I mean, I guess we could. We could talk about these points on a graph. And you know what? Let's actually talk about the points on this graph. All right, we're used to connecting the lines here, and that's what I was going to teach. But I mean, sometimes things aren't like that, right? These are these points on the graph here: 1, 4, 2.5, 10, and 4, 16. Right? Notice how they are not on the same horizontal plane, the same horizontal line. Okay, so this function with these 3 points is not one to one. Is one to one. However, over here, notice how the points looks like 1, 4 and negative 2, 4. They are lying on the exact same horizontal plane. Okay, so they are not a one-to-one function. Now, both of these are examples of functions, right? Because we do not have one x value going to two different y values. So these are indeed functions, but they are not one-to-one functions. Okay, so again, this particular example is pretty easy. All we have to do is just take a horizontal line and just say, boop. Okay, so looking at A, we have a horizontal line that intersects that more than once, intersects more than once. So this is not a one-to-one function. It is a function, but it is not a one-to-one function. Okay, and then of course this particular function, well, it's basically A, but just chopped in half, right? Well, if we chop it in half or restrict the domain, right, something that we have talked about before when we've talked about domain, if we restrict the domain, then yes, we do indeed have a one-to-one function. Okay. Next up, we're going to talk about inverse functions. So let's, before we begin, well, yeah, we'll go put this on the next page, but then I'm going to put a page before this one. Current page. Okay. All right, so let's go back and add a page. Okay, so here it's kind of the hierarchy of classifications that we have here. Okay, so the very first thing we know of in math, I wouldn't say the very first, but just bear with me here. At the top, we have equations. Okay, equations. Right, and from equations we have specific kind of equations will be called functions. Right? These are the hang on. These are the equations uh, who satisfy only one x going to one y. All right. Well, functions can be one-to-one functions, which we saw on the previous example. Oops, just simply one. 1, 2, 1 functions. And that looks like the absolute value of 2, doesn't it? Let's put our little flags on the one there. One-to-one functions. So we have equations, functions, one-to-one, and lastly, we're going to have what's called inverse functions. And bear with me, let me move my toolbar here. Lastly, we're going to have inverse functions. Inverse functions. Okay. Now, again, this is I don't really know how to word this, but it's a hierarchy of classifications essentially, right? So we have our equations. Certain equations are functions. Certain functions are one-to-one functions, and certain one-to-one functions can have inverse functions. Okay, so now let's go back to our inverse function here, and I'm trying to move my toolbar again. There we go. Alrighty, so the definition of an inverse function. Oh, that's one, guys. There we go. Uh, if f is a one-to-one function, represented by an ordered pair, then the inverse function denoted f and then our inverse symbol there is the set of ordered pairs given by yx. Okay, so again, it's just the exact opposite. If we have a one-to-one function xy, the inverse function is yx. And I mean that's the concept, guys. The inverse is exactly what you think it is. It is going to be an inverse, right? We inverse the function. Um, Now, I will admit it gets a little more complicated uh, in terms of the computation, kind of, all right, but it's not too complicated, right? So let's go ahead and look at how we can determine if things are one-to-one functions, okay? Well, on the previous section, we talked about composite functions. So if we take the two functions, f of g of x and g of f of x, well, if we take the composite f of g of x and we get x, and if we take the composite g of f of x and we get x, if we get x for both, then those two functions are indeed inverses of one another. Okay. Now I'll admit this is my least favorite way to go about finding if functions are inverses or not, and we'll definitely go over my favorite way here in a moment. But um, so what we have to do is we need to take the composite of each function. So let's go ahead and denote f of x and blue. No, let's keep the theme here. We'll do f of x in yellow and g of x in blue. Okay, so the first thing I'm going to do is I'm going to find f of g of x. Okay, so I'm trying to find f of g of x. And so in order to find f of g of x, well, I'm going to write f of x, which is 5x plus 4, 5x plus 4. But keep in mind, g of x is going to go where that x is located. So it's going to be x minus 4 over 5 is going to go where the x is located. So let's move this off to the right. And we're going to replace this x with a x minus 4 over 5. Okay. All right, when we do the calculations, we know the 5's cancel. X minus 4 plus 4, well, that's just going to be x. Right? X minus 4, let's write that out actually. X minus 4 plus 4, which is just simply equal to x. And that's exactly what we're wanting. So f of g of x is x. That's good. Now we're going to have to find g of f of x and make sure it equals to x. So let's do that. So g of f of x. So we've got, again, we're going to write g of x, which is x minus 4 over 5. And we're going to replace this x with f of x. So we're going to say 5x plus 4 plus 4. Okay. Well, if we do this arithmetic, it just becomes 5x plus 4 minus 4, or 5x over 5, which is just simply equal to x. Okay. Well, since in both cases, since when I took the composite of both g of f and f of g, in both cases I got an x, I can say that they are indeed inverses of one another. Okay, now I said that this is my least favorite way to do it, so let's figure out my favorite way to do it. And this be it. All right, so finding an equation of the inverse of a function. All right, so most of the time I say, guys, don't worry about these algorithms. You know, you can pretty much, just learn how to do it, and you don't have to memorize the algorithm. This is one of those cases where, I definitely 100% follow along with this, and I follow along with it by actually saying it out as opposed to trying to memorize it, right? Instead of trying to memorize how to make a peanut butter and jelly sandwich, you just do it. Well, in this particular case, I'm actually going to try and memorize it. And while we're at it, I'm going to go ahead and use the previous example as an example here. So 5x plus 4. So f of x is 5x plus 4. So let's go ahead and use the previous example and just kind of follow along. Plus 4. Oh, I messed that up so bad. There we go. All right, so f of x equals 5x plus 4. All right, so step 1, we need to replace f of x with y. So we're going to say y is equal to 5x plus 4. Easy. Step 2, we're going to interchange x and y, which, and by the way, um, I guess the main reason why this is one of the main things that I actually try to follow very, very thoroughly, as opposed to previous algorithms, is because I remember doing this as when I was going through class, and I would try to take shortcuts, and I would just fail miserably. Okay, and so maybe that's why I always take my time slowly with just this particular step-by-step process. But once you do it a couple times, you should memorize it pretty easily. But anyway, step 3, solve for y. So we can solve this for y. We can just kind of in our head, right? We're going to subtract 4 from both sides and divide by 5. So we're going to have an x minus 4 divided by 5 is equal to y. And then it says replace y with f inverse of x. So we'll have an x minus 4 over 5 is equal to y, right? And then, I'm sorry, not equal to y. It's equal to f inverse x. F inverse of x. All right, and of course, I know this. I can essentially just swap sides there. There's nothing wrong with it. Um, it's the same thing as saying f inverse of x is equal to x minus 4 over 5. Okay. Now check this out. There's g of x minus 4 over 5. Okay, so like I said, example 2, taking the composites of each function. Yeah, you can do that. There's no problem with that. I mean, it's useful to know, it's useful to do, all that good stuff. But to me, at least Sherman, if I'm going to verify that something is an inverse function, I would rather do it this way. I would rather take the function and then find its inverse and then be like, oh yeah, this is definitely, so this in the green is definitely what this is, and be done with it. Okay, so let's do a couple more examples there. Let's see, how many? I think we got 5 today. Yeah, so um, find the inverse function. Okay, so just following along with the steps. Step 1, if you recall, is going to be to change f of x into y. So we're going to say y is equal to 2x plus 1. Step 2 is to interchange x and y. Step 3 is to solve for y. So it looks like we subtract 1, divide by 2, so we're going to have an x minus 1 divided by 2 is equal to y. And then step 4 is to change y into f inverse. And I'm going to go ahead and swap them. Okay. So we're going to have f inverse of x is equal to x minus 1 over 2. Okay. Now, again, that's it. There's not much more to it other than that. That's it. So let's do another example. Let's do a little more complicated of an example here. And this is about as complicated as it's going to get for you guys. Okay. Alrighty, so example 4. Again, first step, we're going to change g of x into a y. So we're going to say step 1. We're going to say y is equal to cube root of 5x minus 4. We're going to interchange x and y. Step 3, we're going to solve for y. Now, let's do this a little slower, okay? It's a little slower than in our head that we have been doing. So we're going to say x plus 4, so we're going to add 4 to both sides. So x plus 4 is equal to the cube root of 5y. Okay. Next up, we're going to go ahead and cube both sides. So we're going to say x plus 4 cubed is equal to 5y. Okay, so again, all I'm doing here is getting rid of the, let's actually put that in there. We're going to cube both sides. That's what we got here. And then we're going to divide both sides by 5. So we're going to end up with, we'll put an arrow here. We're going to end up with an x plus 4 over 5. Oh, not quantity cubed, just the numerators cubed is equal to y. And then step 4, like I said, we're just going to go ahead and change the y into an f inverse. So we're going to say f inverse of x is equal to x plus 4 cubed over 5. And, well, that's it. And the last example for this, I think this is pretty, we'll go ahead and snip this as well. I think we can, let me double check here. I think this might be one of those where I want to just snip the actual problem to this. Yeah, let's go ahead and do that. Nah, let's put it on the next page. Yeah, you're gonna have to. We definitely ran out of room there. Guess this is another one where I'm just gonna go ahead and snip the entire problem because I think the idea, the premise behind this is what am I trying to say? Seeing the graph of it is better. Okay, so let's go ahead and look at this first. We see that the graphs of G and G inverse they are symmetric about this dotted line here. Now this dotted line is just simply the graph y equals x, right, or the identity function, right? And the cool thing about functions and their inverses is they reflect about that line. Okay, so if we have, well, on the previous example, okay, we had g of x is equal to the cube root of 5x minus 4. Well, that is this blue line here. Okay, and if we were just to simply look at this, and if we did our one-to-one, if we did our horizontal line test to make sure a function is one-to-one, well, this function is indeed one-to-one. And going back to our hierarchy here, if a function is one-to-one, then it also has an inverse function. So the inverse function will be the function that is symmetric about this line. So if we took this blue line and mirrored it across the dotted line, we have this pink line, which happens to be our inverse function. I actually said that a little backwards. G of x is actually the pink, sorry. G of x is in the pink, and if we reflected it, we get the blue. So yeah, I said it a little backwards, but my point remains. Inverse functions reflect about that line y is equal to x. So if we were to look at this example here, example 5 reads, finding the equation of an inverse of a function with a restricted domain. So if we have a function defined by x squared plus 4, so keep in mind that's just the function x squared shifted up 4 units, or we see it here. All right, but we're restricting the domain for values that are greater than or equal to 0. So this is what our function actually looks like. Okay. Well, if we were to find the inverse function, well, we would do our step 1, step 2, step 3, step 4, and we would end up with this function here, the square root of x minus 4. Okay. Well, looking at, and also, I guess we can try to do this. No big deal, since we have the graph. All right. So we have, trying really hard here. There we go. All right. So if we take the function and this red line becomes the line that I reflect my function about. And again, it's just this dotted line here. Okay, so right here, and if I reflected the function, the blue line uh, across the line that I just drew, the y equals x, well, we're going here at 4, and it looks like we're shooting off like this. And let's put a little, well, let's take that off. We're shooting off like this, okay? Or more precisely, what this is. Right. And so I think that's a pretty cool concept there. Everything that we've said and done so far has really wrapped up in a nice little, like I said, hierarchy of functions, and we see how inverse functions or one-to-one functions have inverse functions, and they are just reflective about that line y is equal to x. Right. And that concludes today's lecture.